Hello, everyone. Today we are presenting our Omdina project, which is a AI-based road inspection system, and it's a collaboration project between the Omdina Mexico chapter and the VIT Bhopal local chapter. Um, and this presentation will be presented by me, Simon, Akshit, and Kurat. Next slide, please. So today our agenda is going to be divided into, as you can see, 9 chapters. First of all, I'm going to just talk about why we did it, what was our motivations, the initial idea for the solution, and the project workflow and the pipeline. And my part will end talking about the data collection and how we have done it. After that, Simone will talk about the model, and then Akshit will talk about the deployment phase, and then Korat will finish by talking about the challenges we have faced during the project, what we've learned, and what's up next. Next slide, please. So why did we do it? So the motivation behind this project is to improve the efficiency of the road inspections, because if somebody can just like take a picture of a road inspection, via like a mobile app or something, and there will be some AI deep learning model using this app to actually like know what kind of road inspection need to be done. This will actually lead to like proven insights, will decrease the infrastructure costs, and will actually improve the efficiency of how the roads can be inspected and fixed. Next slide, please. Next slide, please. So the initial idea actually that we had for the solution, so what we did first is that we tried to go to the internet and find the literature around the inspection of the roads. So what we first went through is actually try to understand how or what are the tools for the object detection and computer vision. So we have like thought about using maps, using GIS techniques, collect some road data images, and stuff like that. But we have realized through some people, and of course Simone was actually the leader of this idea, is that maybe we can just use an existing model, which was the RoboFlow model, to try to actually maybe use that to take our own images and annotate them, and by that solving the problem. Next slide, please. So our project workflow and pipeline was basically that we're going to obtain our images or use pre-existing data sets, and then we're going to annotate these data sets using RoboFlow, as I've mentioned, and then we're going to explore or do our ADA, the exploratory data analysis, and then use the model, which Simone will be talking about, and then after that, the deployment of the model, and Akshit will be talking about that phase. Next slide, please. So the data collection, so what we did, again, yes, we used RoboFlow, but actually the data, so which I'm going to be just showing you in the next slide. So the data that we actually collected, we used around more than 1,700 images. And these data were already in RoboFlow, were in some Kaggle data sets in GitHub. And you can see these all websites that I mentioned in the slide. So we all of us who are actually was doing the data collection part, trying to gather all of these data, all of these images from all of these sources. And after that, we have decided to actually stick. And this was one of the parts that actually we are like a little bit took us some time to try to understand what classes of road inspection systems we need to use. So we agreed eventually to actually use 3 classes, which were the alligator cracks and the cracks and potholes. And these 3 main classes were actually used in the data collections, and then after that in the modeling and the deployment. Next slide, please. So as you can see here in this slide, basically this slide is just showing you like the width and the height of the model. So this is part of our exploratory data analysis. But I really just want to emphasize here how the instances. So if you can see here, you'll see that the most data we have found and the most data we were able to collect were the potholes. So now for the cracks and the alligator cracks, you'll see that the cracks are more than the alligator cracks. And that's a fact because it was really hard for us and for the model. And again, Simon will talk about this a bit, where actually it's hard to differentiate between the alligator cracks and the cracks. So it was much easier for the model to actually say, oh, this is a crack, than actually to say this is alligator cracks. And that's why you will see the instances here for the alligator cracks a little bit lower than the cracks in the potholes. Thank you. And now Simone will take over.
So next slide, please. So the model, what models did we use? Actually, after a thorough investigation, we came up with different models. We started by thinking about using a deep convolutional neural network because our expertise in that sense, we knew that those type of models were used for classification, especially with image handling. However, after a thorough investigation, we saw that there were let's say top-notch models called the YOLO models. As a brief description of the YOLO models, YOLO stands for you only look once, and it proposes using an end-to-end neural network that makes predictions of bounding boxes and class probabilities. So in a nutshell, it divides the image in a grid. It divides in different boxes, bounding boxes, and it tries to classify inside of those bounding boxes, well, the classes that we're trying to classify. How does it work? The YOLO algorithm actually takes an image as an input, and it uses a simple deep convolutional neural network to detect the objects in the image. The architecture that is shown down below, it's as I was mentioning, it's a series of convolutional neural networks that are interconnected, and then at the end they just have a prediction net. So the first 20 convolutional layers of the model, actually they're pre-trained with ImageNet, which is a deep convolutional neural network trained with, I think, more than 1 million data. And by plugging in a temporary average pooling and a fully connected layer after those 20 layers. Then, as I was mentioning, YOLO divides the input image into an S by S grid, which I was telling you. It just divided in a grid, and yeah, starts doing the prediction. So we started with the YOLO v5 because we saw that there were some work done with YOLO v5, and actually there was an integrated labeling file, which was called the label image.py file. However, we'd encounter some problems with that type of that model and with that type of labeling, because when using the label image.py file, when someone did the labeling, yeah, the index of the label was different from one computer to the other, so from one user to the other. So it was a very homogeneous labeling. That's why we transfer our whole labeling, as previously mentioned, to RoboFlow. Once we got used to the RoboFlow, we actually saw that RoboFlow presented us with the tool of using YOLO v8 model. So we investigated a little bit more about the YOLO v8 model, and we saw that it was actually performing quite good. However, we found some downfalls on using the YOLO v8 model from the RoboFlow web app. So that's why we decided to use the YOLO v8 model provided by the Ultra Analytics, and we actually train it by ourselves. Yeah, next image, please. So here are our model results. As I was telling you, the YOLO divides our images in different boxes. So when you see box loss, it's actually how well it performed against detecting the class in that model, right? In that box, sorry. So we can see that our model, for example, in our box loss is constantly decreasing. It's interesting to say that we could have run our model for more epochs. However, the YOLO v8 by Ultralytics has a early stopping criteria, and when some parameters don't change for a certain amount of epochs, it just like stops the training earlier. So yeah, we can see a downcreasing tendency by the box loss and by the class loss, which it's obvious because I was telling the class and the box, they're strictly correlated by each other. And also we can see the precision, how it got how it increases and then it arrives to a plateau of 0.5 by the precision, and by the recall by 0.35. And well, one of the most important metrics that we have to look at in our models are the mean average positions, especially the mean average position 50. And we can see that we arrived to a mean average position of almost 0.39, 0.40. Next slide, please. Yeah, here are some of the results. As I was telling you, we have the correlation matrix. As you can see, our model performed very good with alligator cracks, which is kind of interesting because we thought that having less data about alligator cracks will make our model actually not be that that good at predicting those type of defects. However, it showed a very good prediction ability also with potholes, which was expected because potholes are way different than cracks and alligator cracks. So the model actually recognized them fairly quickly and also with a high precision. And what we saw is that cracks there, our model actually struggled a lot with cracks because the difference between alligator cracks and cracks was like very fade. So our model was kind of doubting about it. We can see in the F1 confidence curve, like an overall F1 is used for how good our model performed in the classification procedure. So we can see a 0.39 is we got like 0.39 to 0.41, which is almost like acceptable, almost good for like a deployable model, for a large scale deployable model. It is considered a 0.5, an already acceptable thing. We think that we could have used more images, or we could have trained our model for a longer training period so we could reach a higher value. In that case, well, we can see that cracks are actually the class that is taking our average down. As you can see, they have an average they have an F1 confidence of almost 0.2, while our other two classes, they get up to 0.4. Next slide, please. Next slide, please. And yeah, as I was telling you, well, we also explored the RoboFlow YOLO V8. However, we encountered some problems with that model because we weren't able to extract the parameters being more precise, the weight and the biases of our neural network to actually apply it on another project. Let's say using it for the image classification web app that we developed. So yeah, with the RoboFlow results, something that it's interesting to point out is that it always started with a hot start, especially with the metrics. As you can see, it started with a 0.4 precision, or like very high precision, and then it dramatically dropped, and then it tried to get another time to that maximum. However, as we were telling our model, it wasn't like that robust, and it couldn't reach that hot start because that hot start was given by other pre-trained models that the RoboFlow website already had. So yeah, it was kind of unfair in that sense to expect that our model would have performed equally as the other models that were trained for many and many other iterations, and more many other for more time than our model. So going next is actually with the deployment of the model.
Next slide, please. Hello everyone, I am Akshay Srivastav, and I will be discussing the deployment of a machine learning model using Streamlit. Streamlit is a user-friendly framework that simplifies the process of building web apps and data-driven dashboards with Python. It provides an easy integration with various libraries, making it an effective platform for deploying the models. We have used the Streamlit Community Cloud and utilized the Python API provided by the Streamlit. This integration allows us to seamlessly incorporate our machine learning model into the web app. To achieve this, we have imported the YOLO class from the Ultralytics library. This class enables us to load a model which is in PyTorch format for the deployment. Next slide, please. Next slide, please. Okay, so as we are aware, a model can detect various anomalies on road, including the cracks, alligator cracks, and potholes. draw bounding boxes around those detections, which makes it easier for us to locate the following cluster. Like in the following image, we can see that the model has perfectly detected the pothole and drew a bounding box around it. Moving forward with the deployment of a model, we have developed two key features that harnesses the power of well-trained model. These features allows the user to input images and videos for prediction. Let us take a look at the demo video and understand it more deeply. Can you play the demo video? As you can see here, in the predict defects, there are two options, images and videos. When a user uploads an image for prediction, we utilize the OpenCV library to read the image file, which is then converted into a NumPy array. This array is passed to predict the method of a model, which generates a list of objects detected in the image. The list includes the bounding box coordinates, class labels, and confidence scores of the detected objects. To visualize the results, we use a plot method from Ultralytics module to draw bounding boxes and detect objects on that image. Finally, the image is converted into a PIL image object and displayed on the Streamlit web app using the image function provided by the Streamlit. By utilizing Streamlit, we have streamlined the deployment process and provided users with an intuitive interface to interact with the machine learning model. They can easily upload an image and see the predicted results in a real time. Now you can see that video. When a user uploads a video for prediction, we call a custom function called process video, which takes a path of the uploaded video file as an input. This function loads the video using OpenCV's video capture function, and each frame of the video is processed individually. The predict method of a model is applied to each frame for object detection. Similar to the image prediction, the plot method from Ultralytics is used to draw bounding boxes around the detected anomalies in each frame. Each process frame is then converted to a PIL image format and appended to a list of predicted frames. To create a new video clip with the annotated frames, we harness the power of FFmpeg. The frames are combined using FFmpeg to generate a new video clip. The temporary video file that was uploaded by a user is removed, and the newly created video clip is saved as output.mp4. This processed video is displayed on the Streamlit web app using the video function provided by the Streamlit. Finally, we hosted the application using Streamlit Community Cloud. We added the requirements.txt and packages.txt files to our GitHub repository, which contains all the necessary packages and modules needed for the web app to run. The Streamlit Community Cloud seamlessly integrates with our repository to host the web app and make it accessible to the users. I would like to call Kurat from here for the next slide.
Um, Hello everyone, I'm Kuratulan. So, as my fellow collaborators have already made you aware with our project aims and objectives, model development and model deployment phase, I'd like to enlighten you all with the challenges we faced, our experiences, and our future plans for this project. So, challenge that we faced. We will discuss three key challenges that we faced. The first one is collecting a diverse and representative data set of pothole images. The second challenge that we faced was selecting the most suitable model architecture for pothole detection. And the third challenge that we faced was ensuring model generalization under varying environmental conditions. So, if we talk about the first challenge, collecting a diverse and representative data set of pothole images is crucial for training an effective pothole detection system. So there is a very important importance of dataset diversity. That is, it gives different lighting conditions, road surfaces, pothole sizes, and perspectives affect pothole appearances. So, what were our methods to tackle this challenge? We used a manual collection. That is, we physically captured images under various conditions. Also, we used various crowdsourcing platforms to collect images from a wide range of contributors. Our second challenge was model architecture selection. So, choosing the most suitable model architecture was very crucial for accurate pothole detection. The key deep learning architectures for this object detection included, we had various options like YOLO, real time, which is a real time object detection suitable for applications requiring speed. Second option was CNN, convolutional neural networks, that captures spatial information effectively and widely used in computer vision. RCNN, region based convolutional neural networks that provide accurate localization and object detection. Our third challenge was model generalization. So, pothole detection systems need to perform well under varying environmental conditions. The challenge was that we ensured that the model trained on one set of conditions can generalize to unseen conditions as well. What were We used different strategies to address this challenge. First was we used a diverse data set in which we included images from a wide range of environmental conditions during training. Second was data augmentation. Synthetic augmentation techniques can simulate various enlightening weather and road conditions. And the third method was transfer learning. Leveraging pre trained models and fine tuning them with pothole specific data can improve generalization. Can we move to the next slide, please? Yeah. So now I'll be talking about our experiences from this. To develop object detection models, we learned how to apply deep learning tools and transfer learning. We developed the object detection model using Python tools, and we also learned the process for picture annotation. So, we also experienced how to work in teams on a variety of projects. Task leaders developed their initiative and fairness in task distribution. Slack was used to teach team members how to communicate task progress in order to complete each assignment. In order to complete every task, collaborators also learned how to clarify issues and offer solutions. Can we move to the next slide, please? Yeah, so now we will talk about what can be our next moves in the development of this project. Using increasingly sophisticated object segmentation techniques, more entities can be recognized, such as traffic signs, signals, and turns on the road, allowing us to fully incorporate all road related characteristics into our model. We aim to incorporate more advanced object segmentation methods to detect a wide range of entities, including traffic signs, signals, and road turns. Additionally, we intend to deploy our model in an embedded system equipped with a camera to detect root faults and cracks in real time. So let's delve into the details, like how can our model actually detect root faults and cracks in real time. There are two ways. First one is enhanced object segmentation. By leveraging advanced object segmentation techniques, we can enrich our model's understanding of the road environment. This allows us to detect and classify various road related features, such as traffic signs, signals, and turns. Through semantic segmentation and instance segmentation, we can achieve pixel level labeling and distinguish multiple instances of the same class, enhancing the precision and accuracy of our analysis. The second way is real time fault detection. To address road maintenance and safety, we propose implementing our model in an embedded system. Equipped with a camera, this system can perform real time fault detection, identifying road faults and cracks as they occur. By leveraging computer vision algorithms and efficient image processing techniques, our embedded system will promptly identify these issues, enabling timely interventions and maintenance action. So, can we change the slide? Uh, Last but not the least, this project would totally not have been possible without the hard work and dedication of our collaborators. So, a very big thanks to our collaborators, which include Akshit Srivastav, Ananya Tiwari, Amir Sharma, Astha Srivastav, Arjita Arora, Aniruddha Kumar, Arpit Sengar, Dhruvil Jain, Enrique Unzueta, Navneet Lamba, Puneet Kaushik, Pushpendra Kushwaha, Poojan Shrestha, Kuratul N, Sergio Reyes, Simone Reynoso, Saurav Datta, Virat Srivastav, and Yahya Ismail. So, once again, a very big thanks to all of our collaborators, and a very big thanks to everyone who listened to us with patience and for your time. Thank you.